Right, thanks. It's my great pleasure to speak here in honor of Dustin. All right, so let me start with, no pun intended, the motivating question. Is to like understand, in some sense, like what we call whale type cohomology series of algebraic varieties. So these should be some functors. So throughout the talk, just for simplicity, let me work with schemes which are separated finite type over the integers, just to fix the setting. And they should be some functors. Go to the derived category of some ring R, some commutative ring. And I mean, one can wonder what kind of axioms should I want here. Like the minimum here, and which I want, and which I want to signify with this kind of whale type here, is that it should satisfy the Kunit formula. So if you have a product of two varieties, the cohomology should be the tensor product, derived tensor product. So this is like including, like, I mean, there's some kind of absolute cohomologies where, I don't know, take etale cohomology, but then also the Galois cohomology acting on it. So some kind of absolute Galois cohomology wouldn't satisfy this. Or like Motivic cohomology wouldn't satisfy this because it's some kind of absolute thing, but many other things do. So what like the examples we know and love. So there is Betti, which is like the singular cohomology of the complex points. There's the Rham, which maybe you should assume X is smooth or something like this, and then maybe in characteristic 0 to make it well behaved. There is etale cohomology, and then empirically there's also like maybe crystalline cohomology, and like a little more recently there's also prismatic cohomology, which nicely interpolates between like at least those three things. So I always like to draw this this kind of two-dimensional picture, which funnily has almost two spec z directions. So one spec z direction is somewhere about the geometry of the situation. So there I usually call my prime p. And one spec z is about the coefficients of the cohomology theory. And so that's what I like to call L. And so then you, I don't know, you have all the primes here. Somewhere you might have some infinity. Same here. And so then, sorry, singular cohomology is something that's defined with integral coefficients. So like it has a full spec z direction, but it's really something that only is something of the complex point. So it sits somewhere at infinity. So singular cohomology would sit here. The Rham cohomology, well, that's defined in any characteristic, at least for something like proper, maybe smooth. But in any characteristic, the coefficients are the same as a characteristic, right? If you work with schemes in characteristic P, then the Rham cohomology also lives in characteristic P. So this kind of sits diagonally here. And then conspicuously, these two lines meet there. And also, this is reflected in the actual mathematics because, like, when you have both Archimedean coefficients and, sorry, when you, like here, this signifies that both the geometry and the coefficients are in characteristic P. And there you have the comparison isomorphism between the Rham and singular cohomology. If you do, next to my list was etale cohomology. So this you can do for any prime L with the L coefficients. And so, for example, if L is 2, this would sit here at L equal to 2 and is defined away from characteristic 2, not just mod 2, but like mod powers of 2, so some kind of formal completion here. And again, conspicuously, these lines meet, and again, this is reflected in the mathematics because over the complex numbers, like singular cohomology tensor ZL is etale cohomology. And this exists for any of these primes. but you should stick away from the residue characteristic because the etale cohomology gets bad there. What else? So there's crystalline cohomology. So crystalline cohomology is something for varieties in characteristic P, which somewhat deforms the Rham cohomology and then somewhat sticks out a little to the formal completion. And then, but with prismatic cohomology, you can somehow fill in all these regions. And this is a picture that I was drawing in my ICM article, in particular in 2018. And basically, since then, I've been trying to figure out how to fill in more parts of this diagram, right? So the goal is like complete the diagram.
Maybe I misremember something, but prismatic cohomology, I mean, coordinate formula is slightly more subtle.
I mean relative prismatic cohomology, not absolute prismatic cohomology. All right. So where to look, or what structure should it so yeah, I'm looking for ways to fill in this diagram, and so where should I look? And so one kind of empirical observation is that in many examples, this functor can be factorized. So you have your category of schemes over Z, always separated of finite type. Let me not write it all this time. And then you go to some other geometric objects, so some kind of stacks over your ring R. And whenever you have a stack, you can just take coherent cohomology. You can take the cohomology just of the structure sheaf. Then of course you get go to D of R. And under very minor assumptions on the stack, this will automatically take products here to tensor products. So this is basically automatically a symmetric monoidal functor. And then the symmetric monoidality you would want is that this functor should commute with finite products, or even all finite limits, as it often does. So there's some kind of curious functor that starts out with one geometric object, which is just a usual scheme over the integers, and then builds some other thing, which is again a geometric object, but now with a completely different base. Let's call it X question mark, which is living here. And in some sense, this procedure should somehow be geometry preserving, like fiber products go to fiber products, and maybe like open emergence should go to open emergence, and so on. So there's some procedure that somehow switches the base field, but it preserves all the geometry. So such functors, X goes to X question mark. Bhagav has introduced the term transmutation for such functors. All right, and so one thing, okay, so the word motive, why it appears in my talk, should be clear, because like Grothendieck and Visage, that's a universal such cohomology theory should be a theory of motives, and I'm trying to somehow approach this from the other direction and not try to build some universal thing by universal properties necessarily, but really try to construct something explicit, which like practically behaves like some universal thing, just like prismatic cohomology somehow periodically behaves like a universal thing, because all the other things you know and love are specializations of it. Right, so this explains the word motives in the title. Now I can also explain the word ring stacks. Namely, because this is a functor that commutes with all finite products, you can send the affine line here over the integers to some stack here, affine line question mark. But if this functor commutes with finite products, then all the algebraic operations we have on the affine line induce corresponding operations on this thing. So for example, I don't know, the addition map. If you run it through the functor, because it commutes with finite products, it gives you a corresponding map on A1 question mark, and similarly the multiplication, and they satisfy all the relations. So this must be somewhat a ring object in stacks. I.e. a ring stack. Okay. So what are some examples of this phenomenon? I think the first one historically is this due to Simpson from the 90s. He observes that, let's say, so this is about the Rham cohomology, and so the Rham cohomology works best if you're in characteristic 0. So let me first explicitly say that this is like a smooth scheme over Q. Then he defines the Rham stack. X to Rham. And so usually this is defined in terms of functor of points. I want to rather like give you the presentation that I usually have in mind when I think about this. So it's a quotient of X where I identify infinitesimally close points. So what you do is you somewhat take the diagonal of X completed, by which, so the diagonal of X completed is the completion of X inside of X times X. So this is a closed subscheme, and you can take its formal completion as a formal scheme, but really as an in scheme here. Yeah?
Do you mean X squared?
X times X.
Just X over there. On the left.
On the quotient.
I mean what I've written, I think. I mean, maybe it's slightly bad notation, but okay, so this is my notation. So it's an in scheme, it's an inductive union of all the nilpotent signalings of the diagonal, and you can form this quotient. And then, I mean, this is very much related, like what are vector bundles on this thing? These are vector bundles on X, together with identifications of all these formal neighborhoods. And so by Grothendieck's classical perspective on modules with integral connections, vector bundles on this thing are exactly vector bundles on X with an integral connection. And like more, or like on the level of cohomology, the coherent cohomology of this is the Rham cohomology of X. All right, and this has been used in many works after this, in particular, like in this Gates-Curry school of geometric Lagrange, that uses this perspective a whole lot to think about D-modules. There's a slightly more, maybe the next one where like people really started looking into this was like in crystalline and prismatic cohomology.
By the way, here X is singular. There is a non-trivial theorem that actually this computes the right algebraic cohomology. So it's, but anyway, we don't.
There are lots of tangents one could go to, but let me not do it. In the case of crystalline prismatic cohomology, I mean, very soon after like prismatic cohomology was introduced in general, both Drinfeld and Butt and Leary realized that it could also be gotten in this form. So there's what's called the stacky approach to prismatic cohomology. Because prismatic cohomology kind of moves out a little bit and also has a comparison to etale cohomology, one can also, and this is more or less the subject of Lucas Mann's thesis, treat at least etale cohomology like over periodic fields also in this manner. Let me make a small arrow to etale. That's by Lucas Mann, but this only works over periodic fields. And then there's one missing on my list, which is Betti. And this actually also works. This is slightly more curious. And it's very much related in one way to this kind of condensed formalism. So, so there's a so we have X of C, which is some locally compact Hausdorff space. And it turns out that there's a general way to take any locally compact Hausdorff space and produce some kind of stack over the integers whose coherent cohomology is exactly the Czech cohomology of this guy. So that's the following funny construction. There exists some kind of canonical functor from locally compact Hausdorff spaces towards stacks over the integers. Let me just again write X maps to X Betti. How does it work? So if you have a profinite set,
What is R in this case?
R is the integers. What do you mean the same? Yes, in the end, I go from Z to Z, but I could really start with a scheme over the complex numbers and then produce something which is a stack over the integers. Because X of C obviously only depends on the guy over the complex numbers. So if you have a profinite set, this is just the limit of finite sets Si. And I can just take the corresponding limit of like Si times spec Z. So like each finite set I can obviously consider as a scheme over the integers, but the finite disjoint union of copies of spec Z. Each of these is an affine scheme, so the limit is also an affine scheme. So if you want, there's a spectrum of the continuous functions from S to Z, which is just some discrete ring. But then there's this funny observation that any compact Hausdorff space can be written as a quotient of a profinite set, where the equivalence relation is also a profinite. And so you can define this in general by like covering your, let's say it was actually compact Hausdorff, by profinite set doing this, and then the equivalence relation you can also do it, and then you can pass to stacks again. Makes sense. Actually, you can also write down the functor of points of this, and it's precisely like continuous maps from the underlying topological space towards X.
So this is an FPQC stack.
FPQC stack. And maybe I should put some finite dimensionality here. It's definitely satisfied in this example, so let me not worry too much about it. And so then, yeah, you can show that the coherent cohomology of this funny stack is precisely the Czech cohomology of this guy. Okay, so that's some slightly curious example. All right. So, okay. But, well, I mean, okay, you just evaluate on the affine line, and then you get the ring stack. Okay. And okay, so then I thought about this perspective more and more, and like in particular in periodic cohomology, like you want to go to the generic fiber, and then things become more analytic. There's also stuff you can do over the complex numbers. I don't know, but for all of these things, I had the feeling that I need to do more and more, make things more and more analytic, which feels kind of strange because the motivating question is certainly like a purely algebraic question. So some kind of I don't know, cohomology series. Like, so there are only algebraic objects on the board there. So there's some kind of feeling that one should look for these things. In analytic geometry. And the goal of this talk is to like recently I've realized a little more clearly why this should be necessary, and the goal of this talk is kind of to explain why. So why analysis? And so evidently the next thing I should talk about is presentable infinity n categories. Okay, so there's a kind of technical intermission in this talk, because this will be necessary for what I want to say. Maybe as a stepping point, like all these cohomology series, they shouldn't just associate to any x some cohomology, but there should really be some kind of Six-functor formalism around and so on. And so over the last couple of years, it's almost starting from Lucas Mancias, I really thought much more intensely about what's this notion of a Six-functor formalism and how best to encode it. And so recently I somehow realized that the best way to encode it is to really embrace infinity 2 categories. And this is what I'm trying to say next. But also critical for this, at least for me, was really to have this notion of presentable ones, which are ones which have all co-limits. So this is a series that's very recent, I think. So there's a paper from Rham and Stefanich from like 2020. And so I also discussed this a lot with some of my PhD students, in particular my PhD student Koaoki. And he explained to me a variant of the definition of Stefanich that I'm about to give. All right, so let's first recall the story when n is equal to 1. So then we have Lurie's PRL. The PR stands for presentable, the L stands for left adjoint functors, or these are the co-limit preserving functors. So what is this? I will not define what an infinity or infinity 1 category is here. I refer you to Lurie. I want to single out the ones that I'm allowing in this PRL. So these are the so-called presentable. I mean, usually Lurie just says infinity, but because I care about the case of infinity n in a second, let me stress infinity 1, where maybe I should also say that infinity means that there are morphisms of like, there are 1 morphisms, 2 morphisms, 3 morphisms, 4 morphisms, and so on. The n means that after this level, they are all invertible. So by infinity 1, you can have non-invertible 1 morphisms, but with 2 morphisms, 3 morphisms, and so on, all the higher morphisms, they are all invertible. It turns out that this seemingly technical restriction makes the theory much cleaner and much easier in many ways. And the functors are the co-limit preserving functors, so they are the ones that admit left adjoints, that are left adjoints, that admit right adjoints. Like usually all the large categories you ever care about, like I don't know, the category of all sets, the category of all abelian groups, the category of all rings, the category of anima, the stable infinity category associated to some ring, and so on and so forth. These would all be examples in there. One beautiful feature of this thing is that you can do algebra within. So this has a so-called Lurie tensor product, so you can tensor two things together. And for example, if you tensor the derived category of ring R with the derived category of some ring S, you get the derived category of R tensor S over the sphere spectrum. So you can really start to do algebra one level higher, where you somehow don't like work with modules and tensor them, but like work with categories and tensor those together. And okay, we might go want to go one step higher.
Can I ask a question?
Yeah.
What did you say about the sphere spectrum?
The initial object in here is what we learned this morning. Is the category. Is the category of anima. But okay, there's also the category of spectra inside there, and this is actually, which is in some sense the derived category of the sphere spectrum. This is idempotent. In general, the tensor product you would be getting abstractly here over the sphere spectrum. Ignore, please. Right, so we want to go higher, so we need to talk about like categories of categories and so on. And so usually at this point, the theory gets nasty because you need to fix universes. One raison d'etre for the theory of presentable things is that it's somehow a way to avoid talking about universes, because in there you really have the full category of sets, not of small sets for some fixed cardinality. And so the presentation I will give does not choose universes. But as an intermediate step, I need to fix one kappa, which is not really a choice of universe, but plays a slightly different role. Let's say you fix a regular cardinal kappa, and actually in practice, the first, like Aleph 1 would be in some sense good enough. So if you would choose the first infinite one, like omega 0, then you would be reduced to finitary things, which is not what you want. But as soon as you allow some countable infinitary things, this is what's good enough in practice. So then you can define a certain, in some sense, subcategory of this PRL, which I will call PR kappa. So these are the so-called kappa compactly generated presentable ones. And those colimit preserving functors that also preserve kappa compact objects. Preserving functors that also preserve kappa compact objects. So like a kappa compact set is just a countable set when this is Aleph 1. Kappa compact object here is just a countable Abelian group or a countable ring and so on. So, and everything is somehow generated freely in some sense from the countable object. This is what we're saying. So, so such a C in here will always be some free construction, some big int category of the kappa compact objects. Let's cover down here.
So what kind of colimits are preserved?
All colimits. Sorry. Colimit preserving functors, but these functors should also preserve kappa compact objects. So if you have a functor from C to some D, this actually just corresponds to a functor on the kappa compact objects that preserves kappa small colimits. I'm using that, sorry, greater or equal to all F1, I should say, because otherwise there's some idempotent completion nonsense. Okay, so then then this whole category is in some sense a union of all these PR kappas. Not quite in the sense of fully faithful embeddings, but in the sense that when you restrict to underlying groupoids, so only regard like the objects with isomorphisms between them, then there's just more and more and more. And so similarly on the morphisms, there's just more and more morphisms. Okay. Any given category will at some point be kappa compactly generated. This is precisely what this presentability says. And at some point, they will also preserve the kappa compact object. So all the morphisms lie at some stage. And so on. And it turns out that in some sense, I actually like this one better. In fact, in practice, everything that's happening in PRL actually happens in the first stage, actually happens in PR Aleph 1. So you might as well stick there. All right, and now here's a curious fact, which is the one that allows you to bypass all universe issues. PR kappa, so that's itself some infinity 1 category, where I don't allow the two morphisms, because that's a more difficult theory. It turns out that it itself satisfies the axioms of being an object there. It is true. So this is basically what lets you bypass all universe issues.
Of course, the number of generators can go up, or the number of the home set.
Yeah, so it's slightly curious. So, like, even the most trivial category, presentable category, like the category of all anima, it's a unit object in here. Within all presentable ones, it's not kappa compact for any kappa. But if you restrict to kappa presentable ones, then it becomes kappa compact. And then actually you can basically show that this and other similar things actually generate the whole thing. Okay. In fact, it's symmetric monoidal, so it's actually a commutative algebra object in PR kappa. Well, and now we can do algebra one level higher. And define two PR kappa, like what you think of as kappa, like kappa presentable infinity 2 categories, as being like categories enriched in categories. Yeah, but I mean, like, I think this is the first instance where you have a category of categories that contains itself. Okay. It exists. Okay. Kappa presentable infinity 1 categories. You can just define this to be modules over PR kappa in PR kappa. So having this module structure basically means that there is some internal Hom in particular. So between any two objects, if you have an object in here, then between any two objects, there's an object in here as morphisms.
Please use different notation for PR kappa. I mean,
no. And I mean, it's always true that when you have any algebra object, commutative algebra objects, then the category of modules is itself a commutative algebra. So this is itself a commutative algebra in here. So in particular, you can iterate. And for any n greater or equal to 1, define a series of infinity n plus 1. The great thing about this is that these are like all just like usual presentable infinity 1 categories for which you have a well-established foundations with some extra structure that's also of the well-established sort, that it's just about commutative algebra in here. You might object that as I defined it, these n PR kappas, they were just infinity 1 categories, but really secretly, like between any two n categories, there should be an n plus 1 category of functors. But, I mean, each of these is symmetric monoidal. So in particular, each of these is a module over itself. So, symmetric monoidal. So it's a module over itself. So each of these is canonically an object in there, which is n plus 1 PR kappa. So each of these canonically refines to an object in infinity n plus 1. All right, and so for me in practice, I will probably just stick with kappa equal to all f1, and everything is already good. Let me state it as a conjecture that when you change kappa, so you take n PR kappa, then again, this not in the sense of fully faithful functors, but in the sense that there are like more objects and more morphisms, it's contained in the next one. And
do you have a map in your?
Yes, there's definitely a map. Because like if you have a module in PR kappa, like PR kappa maps to PR lambda, so you can just push it forward, but then you can also base change the module structure.
And what does the conclusion mean? It means that on isomorphism.
Like if you pass to the underlying infinity groupoids, it's fully faithful. If you take functors from delta 1 into there and then pass the underlying groupoids, it's fully faithful and so on. And so if you want, you could then define a completely canonical series that's independent of any choices as a union in the sense of all the PR couples. So you just collect more and more objects which are like more and more difficult presentations and more functors that have more and more difficult presentations. All right. Right, so this gives you a way of thinking about like categories of categories and so on without worrying about universes. And without where technically you don't need new foundations because this is really easy to formalize within the existing framework that Jacob Leary has provided.
So sorry. So here I should understand functors as the Lex functors, whatever. I mean, which one should I think of?
Lex functors. Like if you have two categories and they're I'm still confused by higher categories, but so let me now really try to answer the question. Like there are different ways to define what a morphism of two categories is, and the question was which kind of morphism does this really correspond to? No. Yeah. All right. All right. So why did I say all that? So because we're really interested in six-functor formalisms, and I mean there's and six-functor formalisms has these pullbacks, these functors, these exceptional push forward, complex support cohomology functors, and so on. And they should satisfy base change formulas and so on and so forth. And there's a lot of compatibility isomorphisms implicit in this. And for a while, I was extremely confused about a good way to encode this. And there has been work on this by Yifeng Liu and Wei Zheng, and also by Gates-Guerrier and Rosenblum. And Lucas Mann has kind of synthesized these definitions. So let me mention all the names. A six-functor, let's say a presentable one. Is a Lex symmetric monoidal functor. From the category of correspondences, like your category you're interested in this case, schemes separated of finite type over integers, towards Lewis category PRL. And so here he takes just the product of varieties, and here he takes a tensor product. So you send any x to some d of x. And the Lex symmetric monodality means that there's some kind of exterior tensor product. So the derived category of x1 tensor the derived category of x2 maps to the derived category of the fiber product. And I really started to think about this in some detail, and turns out that there's a surprising amount of arguments that you usually just do an etale cohomology or something like this that you can actually carry out in the framework of such an abstract six-functor formalism. In particular, there's a way to prove punctual duality, which usually is like some highly non-trivial theorem in etale cohomology, where you need to fiber into curves, prove Deligne's fundamental lemma and so on. But Bogdan Zavyalov gave a very nice account of this, where you really just have to do one very simple computation for the affine line, and then you're done. Everything else is just category theory. But then even more recently, as I started to embrace infinity 2 categories, I realized that there's actually a better way to think about this using infinity 2. And that's the following. So one thing I somehow didn't like about this definition is that it's just lax. And I told you that I really want series that are of Weyl type which satisfy a Kuhnert formula. So ideally I would really like this functor here to be an equivalence. But it isn't, in etale cohomology somehow it isn't, and so on. So, for motives, the Rath-Kadif motives, it certainly isn't. So that's bad. I think that for thinking like in the Betti setting it would actually be true. In the Rham setting it will also be true. In the prismatic setting it will also be true. So yeah, so it's like etale, that's bad. Motivic, that's bad. Certainly we'll now center about this word whether I want lax or strict there. Right, so but it turns out that you can always rescue being symmetric monoidal at the expense of going one categorical level up. So, yeah, so here's some kind of correspondence. I first saw a statement like this in Lurie's paper, actually on the cobordism hypothesis, where you can, so let's say C is some symmetric monoidal infinity 1 categories. So the case of interest being probably this one here. And then here on the one side you can consider these leg symmetric monoidal functors. Sorry. No, I don't know. Yeah, let me call this key here. To PRL is the product. And on the other hand, you can consider strict symmetric monoidal functors. Let's call them F. From C towards, let me call it C double, towards some symmetric monoidal presentable infinity 2 category. And then there's some kind of forgetful functor here, which takes any f to the functor d, which takes any x to the homomorphisms from the unit into f of x. So basically, the only thing you're remembering out of your infinity 2 category are like the morphisms from the unit, which has infinity 1 categories. And it turns out that this has a left adjoint. Meaning that for whenever you have such a thing, you can build an infinity 2 category, symmetric monoidal guy, where the Kuhnert formula becomes true, where it becomes symmetric monoidal, and you can somehow do this in a free way. All right, so how's my time management? maybe I should actually say that. So, so this diagram is actually isomorphic to the following diagram. So there's like usually when you have a category, you can build the free category generated under colimits by your given one, which is exactly by the Yoneda lemma like functors into sets, or if you work infinitely category, functors into anima. If you use the free infinity 2 category now on C, then similarly you should take the functor category to PRL. So this is a free infinity 2 category, presentable infinity 2 category on C. And now you map to some guy here, and so then you precisely have the datum of a fiber functor. And it turns out that such Lex symmetric monoidal functors, well, they're in particular they're functors of let me write. I may have confused some of my ops. Okay, let me ignore that. Turns out that, well, there are some objects here, and the Lex symmetric monoidal structure precisely gives them the structure of a commutative algebra in this guy. So these are precisely the commutative algebras in this functor category. And I should correct this by passing somewhere to ops, but I'm now confused where I should do that. And if you have such a guy, then in one case you can just pass to the endomorphisms of the unit in C, which becomes linear over this guy. And the other case you can pass to modules. And so this procedure also tells you how to build this. So you regard this datum as a commutative algebra in this infinity 2 category of functors, and then pass to the category of modules. All right. Why am I saying all that? So all right. So what's the point here? So we're trying to like figure out what the kind of universal six-functor formalism or something like this is. And well, there's actually already an answer to this. So there's a theorem that these are the Motivic six functors. So this is actually by a theorem that's, I think, due to Galois. You can characterize this as the initial six-functor formalism. And then you just ask for certain properties, such that, for example, you want that if F is a proper map, then pullback has a right adjoint, which is still in PRL, so it's column preserving F lower star, satisfying base change in the projection formula. Or if F is smooth, then it should have a left adjoint, satisfying base change in projection formula. And then there's, I don't know, there's probably some excision that you might want, some A1 invariance. I mean, these are all conditions, A1 invariance, and you might also ask that the Tate twist is invertible. And I hope I didn't forget some important condition. And now you can run this machine and build some symmetric monoidal infinity 2 category. of motives over Z, or you could also do this over any base. And so let me vaguely describe how this is formed. So the generators, so how to think about this. So the generators are like, let me draw some bracket X, where X is any separated scheme finite type over the integers. And X tensor Y is actually identified with X times Y is the tensor product of them. So the tensor product is extending the Cartesian structure on these guys. But also, like the correspondence is actually mapped towards motives. There's actually a small subtle point here whether I want this as a datum or just as a fact that there is such a thing. And actually, I don't want the datum. I only want the observation that it exists. But this means that any X is actually dualizable because it's already dualizable here. And the dual of X is identified with X. And so this means you can also compute what the homomorphisms are between X and Y, because this is identified with the homomorphisms from the unit to the dual, but the dual is the thing itself, so it's X tensor Y. And this should be precisely by this correspondence being given by the derived category of motives on X times Y as it comes out of this theory. And basically, this tells you the structure of the whole category, because everything else is somehow generated by these under colimits. No, but I assume excision, so you can always stratify into smooth things anyways.
So you know that you said that the dual of X is X is dualizable with dual X?
Yeah. I say that. But in particular, like at this level, the Kunit formula becomes true again. And now suddenly there are a lot of fun observations about this. That actually, this can be made more concrete again. And maybe the most critical observation is that you don't actually need this large, like the thing that makes the usual theory of Wolowski's motive so difficult is that the category is generated by like all smooth schemes over the integers. But I mean, there's a whole lot of them, and so this makes it very difficult to control. And here, a priori, we have the same problem, that we need all these schemes as generators, and that's huge. But it turns out that actually just the ANs generate.
Are you presupposing some kind of stability?
No. I mean, I wouldn't even know what it means at this level. I mean, you can ask that all the morphisms are stable. Yeah. Okay. Sorry, maybe I should say that. Yeah, so morphisms are stable. Thanks, I missed that. Yeah. So why is that? Well, certainly the affine ones generate. So maybe by excision or something. I mean, that's a small thing. But then, whenever you have an affine thing, you can embed it into AN. And then, there's definitely...
Sorry, generate in what sense?
As a presentable infinity 2 category. Actually, under retract is good enough. And I don't know. I upper star. I mean, you have a pullback, but you also have I lower star from X to AN. I mean, it's a proper map, so it should have this right adjoint, which is still somewhere in this category. And then this means, and then I upper star, I lower star is the identity as a map from X to X. And so you've written X as a retract of AN. this is great. For example, it implies, what else did I write here? And you can use it to show that whenever you do the same thing for any other x, then a priori this is again some new complicated thing that you have to build out of x, but actually no. Relatively it's extremely easy. You can just take the modules over x, which is a commutative algebra, in the motives over z. So relatively it just reduces to algebra in this one thing you have to construct. And this also implies that at this two-categorical level, like suddenly the category of motives satisfies Kunit. So if you take motives over x and tensor it with motives over z, motives over x prime, this is just motives. X times x prime. So suddenly all the Kunit you ever wanted becomes true. And you have an explicit set of generators. It implies yet more, basically this observation on the ANs. It means that so a priori we define this as something that's generated by all the schemes here. And then we were just putting conditions. So in the suitable senses here, it's just a localization. But then we can do the smaller thing, where we just generate by all the ANs, by all the affine lines. These already generate, and if you're careful enough, you can show that you can trace all the conditions you need just in conditions out of there. So this is also a localization. All right, so I started 5 minutes late, so I was allowed to go 5 minutes overtime already. So I have at least 3 minutes. Yes?
How do we invert P1 last step?
I mean, so once you have all the ANs, you can build all the other objects you need. You can build like all affine schemes as fiber products of affine spaces, and then you can glue. Once you've asked for all your left and so on the joints. I mean, also inverting P1 is also the same as inverting GM and so on. I mean, yeah, you can build all the other ones and then ask all the conditions. All right, so this means we have a new answer to the following question. What is the realization of motives? The usual answer would be that, I don't know, you have your derived category of motives on some x, and then you look for some tensor functor to the derived category of modules over some r. But actually, you should be looking for much more, because this is where things start to behave well. They start to behave well once you go one level up. You should really be asking for a realization one level up. So for a tensor functor of symmetric, monoidal, presentable, infinity, two categories, to the thing one level up here, which is like the theory of d of r linear presentable infinity categories. All right, so now I know what I'm looking for. Finally, I'm looking for such tensor functors to some d of r's. And finally, I can kind of explain why analysis is needed. Namely, analysis will be needed because I expect that there are extremely few such functors if R is a usual ring. But my hope is that there will be much more such functors if R is an analytic ring, because then you have some more room to play with. And why? So here, like, so expectation. There are few such functors, few such two categorical realizations. For usual rings R. but hopefully many more.
Can you bring the tensor function there to something with x and the right?
I mean, this x and this r, they have nothing to do with each other.
What is the subscript d of r? It means PRL.
Well, d of r is a commutative algebra object, and here, so you can take modules. So maybe I should write that. But hopefully for analytic rings. And so to substantiate this hope, let me explain the case of the Rham stack. And okay, I'm sorry for going over time, but I should say at least that. So you might hope that if you do motives over Q, that then you can, well, you can definitely write down a functor to Q linear presentable stable infinity categories. So now suddenly the base and the coefficients are the same, but that's because I'm someone in the Rham setting. And where you send any x to the derived category of the Rham stack. You might think that this should be a functor. It definitely satisfies the Kunit formula. So the d of x to Rham tensor d of y to Rham is actually d of x times y to Rham. So this is great. So this is used extensively in the work of Gates-Greer and so on. But it's not a functor of infinity 2 categories. So it doesn't qualify as a realization. And what's the issue? The issue is that in motives, you have the open immersion from A1 into P1. And this has a left adjoint. J lower shriek. And adjoints are preserved by all functors of 2 categories. Like an adjoint is defined an abstract notion in a 2 category. So this must be preserved by the functor. But J upper star from the derived category of P1 to Rham to the derived category of A1 to Rham does not have a left adjoint. I mean, if it had a left adjoint, it must commute with limits. But here we were just algebraically inverting a function, and this doesn't commute with any limits, infinite limits. So this is not a realization. Instead, what we really need is that after you pass through this world there, this must be an open immersion in the sense somehow as we defined in the course, that it really has a left adjoint satisfying the projection formula and everything. And so yeah, but if you send any x to, like, you first base change to some non-Archimedean field K, or C, or Q Laurent series T, or something like this. And then you take the analytic Rham stack of that. The analytic Rham stack, as it was kind of appearing, maybe at least implicitly in our TSS talk, where what is the analytic Rham stack? It is x modulo the over-convergent neighborhood of the diagonal. So you take functions that converge in the small neighborhood of the diagonal and mod that out. And now somehow it's the case that the map from the affine line to the projective line is really this kind of analytic open subset of the P1, for which the J upper star does have a left adjoint. So this works. And so this is giving you this extremely highly structured 2-categorical realization functor on motives. And yeah, to get that, you need that open emergence go to actual open emergence in this categorical sense. That basically never works in algebra, but it usually works in analytic geometry.
you said, I mean, there's this theorem of Drew-Gallor that in their pullback formalisms, this Motivic six-functor formalism is initial. And how does this construct me at infinite comma 2 category?
Well, I mean, you start just with this thing up there, right? You start with a free guy generated by all these, and then just enforce all these things. Basically, in the presentable world, you can just put conditions and it will automatically freely generate a new thing. I think one thing I forgot to say, by the way, I said that something is given by ring stacks. So what does it take now to give such a 2-categorical realization? Well, a priori, again, you need to specify what it does to all the x's. But again, because the affine spaces generate, really the only thing you have to specify is where does A1 go? Because, I mean, then A and go to tensor product, so everything is already determined by where A1 goes. And A1 goes to, well, the derived category of a ring stack. I mean, it goes to a commutative algebra object over D of R, the presentable things over D of R. Such things usually come from stacks via some kind of Tannaka duality. And if it does come from a stack, then the structure you need to put in is precisely that of a ring stack, because you precisely need to make this functorial like in all the polynomial maps within affine spaces, which exactly gives it the structure of a ring stack. So such 2-categorical realizations, they are precisely, at least if you take C here, they are precisely classifying ring stacks with the properties that are needed that it actually defines such a realization.
So with your new definition at the end of the day, does this mean that because like the, say, solid theory exists, that all of a sudden usual coherent cohomology with structure sheaf counts as a Bay cohomology theory?
Well, it doesn't satisfy excision and so on. So,
I see.
yeah.
Okay. So,
but I mean, you can be a bit, you can be a bit more lax about which axioms you want. But it's,
okay. But okay, so you're wrong. Okay, I understood. Thanks. More questions?
At some point you fix the cardinal K. I mean, how does it enter in the pictures in this final part? Sorry.
Not at all. I mean, take any kappa, take the union, stick with kappa out of 1, it doesn't matter. Okay. I mean, all the constructions that are really happening are at most countable here, so it doesn't really.
Okay, so in your last example, if you take K equals to Qt and takes a coherent cohomology of this analytic Rham stack, what kind of cohomology theory do you get?
It's just the usual Rham cohomology.
In which sense? The rich analytic sense?
Well, I mean, if this is an algebraic variety, then this is the Rham cohomology doesn't really care about which precise.
You mean varieties without smoothness?
Even without smooth, I mean, because this satisfies excision, so yeah. I mean, so it's I'm not sure what the Rham cohomology of a singular thing is. If it's the one that's somewhat defined by passing to a smooth hypercover, then it's.
No, but
this definition maybe if X is smooth, I should have said, yeah.
How do you recover algebraic the Rham cohomology over Q?
Well, I mean, this construction can be done, I don't know, with this stack of norms basically already. And then the usual Q vector space embed fully faithful into coherent sheaves up there, so it kind of determines it.
So I wonder whether towards, for example, this higher partial homology, whatever, an example of something like
maybe, yeah, I don't know. Mm-hmm. Well, no, I mean, it will never satisfy excision, yeah. But, okay, I mean.
Can you maybe precise what you mean by, so you had A1 invariant, right? So how does the Rham stack satisfy any sort of A1 invariance?
Sorry, I don't enforce it somewhat 2-categorically. I mean, I definitely don't want to contract A1 in the 2-category. I mean that if you, so you have A1, F to the point, and I said that pullback has a left adjoint, right? And so this in particular allows me to define an F lower streak of A1, which will be, I mean, sometimes an endomorphism of the unit. And I asked that, and it will probably map to the unit, and I asked that this is an isomorphism in here. I mean, it's the usual thing one does when one defines motives. That Yeah, well, I mean, because smooth things have left adjoint, you can use any smooth guy it defines an endomorphism of the unit, which is the usual Motivic category.
Or you want some co-unit for an injunction to be an isomorphism.
Yeah. I could also ask that, right? I could also ask that this composite, it maps here, maps isomorphically to the identity. But because of the projection formula, this is actually just tensoring with this one, so it's enough to do that.
What's the characteristic of the field K? Can K be a characteristic?
Yeah, I mean, the Rham theory always works better when you're in characteristic 0. That's why I had these examples. I mean, you might wonder whether over the integers. Yeah, I mean, if I really want something on motives, I should probably stick in characteristic 0.
Sorry, another question. Can you tell, like, if you apply this analytic Rham to A1 and look at modules of that, can you tell what relation there is to G modules on A1?
So you should read this paper of Juan Esteban Rodriguez Camargo about this. He just last week or so put up a paper on Archivic precisely about this analytic Rham stack over like periodic fields, I guess. And it's there's a theory of Ardakov and Watsley of like these D-cap modules. You know about it, and it's basically recovering exactly the theory of D-cap modules. I mean, some bigger version of this because there's like a large quasi-coherent category here, whereas they consider some kind of finitary objects. But
yeah, question. So, if I understand this correct, this construction correctly, so the idea is to be able to analyze and construct better cohomology theories for varieties, and somehow like at the end we want, the only thing we need is somehow how to realize the motives. So I got stuck somewhere trying to follow. So why does it go wrong with excision? So you said something about this.
Well, I mean, usually what you ask for like motives is that whenever you have some variety X and some open subset U and some closed subset Z, then the derived category of X has some kind of semi-orthogonal decomposition into the derived category of U and the derived category of Z, which is something you can. And we were discussing some other examples. What this D of X might be. For example, you might send it to just the usual theory of coherent sheaves on X. But the usual theory of coherent sheaves, this would never, like, I mean, these are R1 over F modules, these are R mod F modules, but R is some, like, R mod F to the n is not part of, like. I'm just saying that in coherent, like, the derived category of ring R cannot be recovered formally from the derived category. It does not admit the same orthogonal decomposition into the derived category of R1 over F and the derived category of R mod F, so it doesn't work.
So yeah, but now we don't consequences like the invariance under nilpotent thickening.
In particular, there's invariance under nilpotent thickening.
So that if you take into
suggests that you could allow for more general. I mean, your starting category schemes, but if you use an analytic spaces, as in the course, I mean, you have more rooms, right? I mean, for example, there are different structures on A1, even over Z, and then.
Yeah, I mean, there's all sorts of variants one could do, but maybe like the motivating question for me was to find realizations for motives over the integers. So, but I mean, of course, I mean, there's also this work of Ayub and then others, Vetsani and so on, where they somehow work with rigid analytic varieties instead, and then you can play the same game. And that's basically how always these categories of motives are defined nowadays. That you, and in some sense, I think one can give a cleaner definition of what these things are if you directly work infinity 2 categorically, because then you really just take this functor category, this thing freely generated, and then enforce all the things you want. Smooth maps of pull, left adjoints, and
Okay, so like the excision property somehow boils down to.
If you think about the stacks, like, I mean, you now want some other stack, where this U becomes an open subset and the Z becomes a closed subset. And this already means that, I mean, this would never be true for the kind of usual algebraic stacks you would envision. Because, I mean, it means that, yeah, basically open emergence, that means there must be some J lower Schwick functor on the level of coherent sheaves. And this virtually never exists in usual algebra. But it does exist in a lot of cases in analytic geometry. But it also means that somehow Z must be, like the thing associated to the closed subscape Z must somehow always overconverge. And so, I mean, it's telling you a lot about how these stacks must look like already. So I have a much clearer vision for what I'm looking for now.
Thanks for highlighting this again.
So, in this case, there is nothing particular about well cohomology. Like, we can get something that uses K-theory, or it models over K-theory. Your modules contain everything, right?
I mean, if well signifies for you that R is a usual ring, then no, I mean, you can take any infinity ring here. I don't, yeah. But, yeah. You could take any symmetric monoidal category if you wanted to. In the end, like, maybe one expects that motives are something which have a motivic T structure. And this should be somehow related to the fact that you can really find many of these realizations where R actually ends up being a usual ring.
But do you expect somehow that, so in that case it fixes a categorical level, I say, it's like it's categorical level 2. Do you expect by growing the categorical level, you're actually...
No, I mean, it won't help going higher up. So basically, I mean, you could also consider like commutative algebra objects in presentable infinity n categories for any n. But basically, you can always go from one step to the next by passing two categories of modules. And this is actually fully faithful embedding. So for each one, you can somehow ask whether it secretly was a category of modules already over something. And so in some sense, you're enlarging the word that you're looking at when you increase n. And then you can wonder somehow at which step do you expect things to somehow be already well behaved. And I think this discussion is precisely saying that for motives, it's step 2 where things are already like well behaved. And after this, you would just get more and more just categories of modules, and then it wouldn't really tell you anything new. I mean, so you could pass the commutative algebras on both sides, but this would just be the same datum.
I know, but you could also try to get this mod Z categorical level higher.
But I think it would just be just modules over this one. Or at least I don't see what new thing you could possibly get.
So you mentioned that this thing it doesn't work naively for in the algebraic setting. But what about some sort of because in classical situation the link considers some sort of pro-coherent sheaves, whatever.
Yeah, so there would be a cheaper way you could try to salvage the Rham stack business, which is like in some sense this D-module six-functor formalism looks closer to the usual thing if instead of incoherent sheaves you take pro-coherent sheaves. But then you're leaving the world of presentable categories. So it will also not define a tensor functor. So if you want a presentable, you should do some kind of int pro, but then the tensor product would tensor these pro things together in an algebraic sense, and it wouldn't give the right thing. So there would be a different thing when you somehow take some kind of solid Rham stack. There would also be. So you could actually define something over Q. You could take over XQ, there would be some kind of ultra-solid structure, but you can also define some kind of somebody to know this is box. This really lives over Q and has all the properties, so maybe there's a different question to the question somebody asked. Yeah, so I don't see any way of like making the Rham cohomology into such a functor that doesn't involve somewhat using some of our analytic geometry.
Doesn't this work? I'm not sure how to do it using the Rham stacks, but if you use the usual theory of the modules, does it work if you restrict to holonomic objects?
It's not a presentable category. As you mean intolonomic. No, but then it doesn't satisfy the Kunit formula, I don't think. That's usually a etale cohomology also satisfies the Kunit formula, and the intolonomic would be more like the etale setting. So to get this usual, where is it? This property there, you really need to pass big categories of D modules, but yeah, then you don't have the left adjoint anymore. So.
If there are no more questions, let's thank you.
Sorry.
So I'm charged with making some closing. Well, thank you very much to the 4 speakers for agreeing to come here and giving those really nice talks. I want to say thank you to the Tondeur for giving the donation that gave rise to all of this and this nice day that we've had here. And I want to thank everybody who came for coming and participating.